We're going to go through this worked example. So the question is, calculate the missing values for the circuit shown. We're told to assume that the bulbs are identical to each other, and we're given two bits of information. That voltage number one, this one up here, is 3 volts, and the ammeter reading at ammeter number 2, this one, is 0.2 amps. Now, there looks like a huge amount to calculate here, and it can be a very intimidating question to approach, but actually it's much simpler than it seems. And although the question says calculate, you don't necessarily need to do a sum to work out each thing. There are a few things that we do need to know. So we need to remember our Ohm's law equation, which is voltage is equal to current times resistance, or we can rearrange that as needed. We need to know how resistance behaves in series, so you add the resistors up to get the total, or in parallel, where you do 1 over each individual resistance, and that will give you 1 over the total, and you can then rearrange that equation as well to work out the total resistance. The main things we need to know for the first parts of the equations or the question is how potential difference behaves in series and in parallel, and how current behaves in series and parallel. So we're going to start off with potential difference. So we know that in a parallel circuit, the potential difference is the same on each branch. So each branch of our circuit is going to have the same total potential difference. So if I know that the voltage being supplied by my power source is 3 volts, then it must also be true that the voltage on branch number 2, which just has one component, is also 3 volts. I don't need to do a sum to calculate that, because that's how potential difference behaves in a parallel circuit. Equally, that I know that across the whole of branch number 2, these two voltages combined must also be 3 volts, because in a parallel circuit, the voltage across a whole branch is always the same as that given by the power supply. So then it's a matter of, well, how do I work out voltage number 3 and 4? Now, in the question here, it tells me to assume that all of the bulbs are identical. So I can make the assumption here that the voltage is going to split equally between these two components. And so I know that the voltage at position number 3 must be 1.5 volts, and the voltage at position number 4 must also be 1.5 volts. We now know the voltage at every different position in the circuit. We haven't had to do an actual sum or calculation to work that out. So that's just about being able to apply the rule that we know that potential difference in a parallel circuit is the same across each branch. Now, if we move on to current, we know that in a parallel circuit, the current is divided between each branch. And we know that if a branch has a greater resistance, it will get less of a share. And we also know that if a branch has a lower resistance, it will get more of a share. Okay. Now, again, an important part here is we know that all of these bulbs are identical. So even without calculating resistance yet, we can assume that this branch of the circuit is going to have half the resistance of this branch of the circuit. Branch 1 contains 1 bulb, branch 2 contains 2 bulbs. All of the bulbs are identical to each other, so we can assume that this would have twice as much resistance. In series, the resistances add together. So this branch is going to have twice the resistance that this one does. Okay, now we know that branch number 1 is allowing 0.2 amps of current to flow through it. So if branch number 2 has twice as much resistance, it's going to allow half as much current to flow through it. So we can therefore assume that the current here is going to be 0.1 amps. Again, we don't need to do a sum to calculate that, we're just applying the rules. If we are then looking at the current at position number 1, now we're thinking about, well, how does the current behave in a parallel circuit? We know that in a parallel circuit that the current is split between the two branches. So when those two branches recombine together, those two parts of the current will be combined. So the current at position number 1 must be 0.3 amps. So again, we've not had to write out a sum to work these things out. We're just applying the rules for how we know current and potential difference and resistance behave within series and parallel circuits. Now, to work out the resistance of the different branches, we are going to have to use some equations. This is where we're really going to have to start putting numbers into a calculation. So I'm going to treat each branch separately first, and then we can look at the total for the whole circuit. So to start with, if I want to calculate resistance, then I'm going to be doing voltage divided by current. That is how this equation is going to be rearranged to allow me to calculate the resistance of an individual component. So on branch number 1, I have 1 bulb. I know that the voltage at this position was 3 volts, and I know that the current at this position was 0.2 amps. So the resistance of branch 1 is going to be equal to 3 divided by 0.2, and that gives me a resistance of 15 ohms. Now on branch number 2, I have 2 separate bulbs. Now there are 2 ways I could think about this, and they're both going to give us the same answer. So I'm going to write out one and then talk you through the second. So we can plug our numbers into this calculation. We know that the total voltage across branch number 2 is 3 volts, and we know that the current flowing through branch number 2 is 0.1 amps. So we could also again plug our numbers into this calculation, and this time we will be doing 3 divided by 0.1, which would equal 30 ohms. Now there's a second way that we could get to that same answer, and it relates to this, that we're told that all the bulbs are identical. So branch 1 contains 1 bulb, so we know that that 1 bulb has a resistance of 15 ohms. We know that in series, the total resistance is equal to each resistor added together. Now on branch number 2, these 2 bulbs are connected in series to each other. We know those bulbs are identical to this one, so we could have just done 15 ohms of resistance for this bulb plus the 15 ohms of resistance for this bulb, and that will also get us to 30. Okay, so we're showing in 2 different ways that we could get to this final total. Now the last part is to calculate the total resistance of the whole parallel circuit. So I'm going to need to use this final equation here. So I know that 1 divided by my total is going to be equal to 1 divided by the resistance of branch 1, 15, plus 1 divided by the resistance of branch 2, 30. And that is equal to 1 over 10. Okay, but that tells me 1 divided by my total resistance. If I want to convert that into a total resistance, then essentially I'm going to rearrange my equation so that R is at the top of my fraction rather than at the bottom. Okay, we can almost think of it as inverting the fraction, because what we know is 1 over R T is equal to 1 over 10. So RT over 1 would be equal to 10 over 1. And 10 divided by 1 is 10 ohms. Okay, now I can be fairly confident that this answer is correct, because something I also know about a parallel circuit is that the total resistance of the circuit is going to be less than the resistance of the weakest resistor. Now, all my resistors are the same in this case, and they all have an individual resistance of 15 ohms. So the fact that my total resistance is less than that suggests that I've calculated it correctly, because that is what should happen in a parallel circuit. Okay, so there's lots of different information there, but we can work out all those individual qualities, or quantities I should say, by looking at the information in our equations and by understanding the rules of how resistance, voltage and current behave in parallel and series circuits.